a little bit. I love the non-committal. It's good. So it's cube root of x minus 3. So you're supposed to graph this and give its domain. Oh, just give its domain and range. I see. Got it. So what's kind of the base function? What's the function that's dictating everything here? The shape is kind of dictated by which aspect of the function? The cube root. Yeah, the cube root, right? So did Mrs. McCullough have you memorize what the cube root function looks like? Oh, not yet? Oh, okay. So if you were to graph the cube root function, do you understand what cube root means? You know, theoretically, I'd imagine you do. What's the cube root of 8? 2. Cube root of 27? Cube root of 216? Good job. Yes. Could you make a table and connect the dots and get a picture of what this looks like? Yeah, if you wanted to make a table, you could. If you graph the cube root function, the cube root of 1 is 1. The cube root of 8 is 2. What you end up with is something that looks like this. Looks like this S-curve kind of thing. What's the domain? So this is just if you eliminated that. That's what the function would look like if there was no minus 3 involved. The larger the number you plug in, the bigger it gets. Are there any numbers you can't plug into the cube root function?
Can't be less than 2.
You sure? By this function, by the graph what I just gave, does that graph have functions that are, does that graph have values, have coordinates that have x values less than 0? Yeah, so this graph seems to say you can. Well, think about it this way. Just go back to a number you know, -8. What times itself 3 times is -8? You can take odd roots of negative numbers. You can't take even roots of negative numbers. You can take odd roots. So you can take a 5th root or a 7th root of a negative number. So are there any values you can't plug into this?
No.
No, there are not. So therefore, what's the domain of this function? Yeah, so you could write it as -infinity to infinity. Another way to say that is all real numbers. And another way to write that is like this. That symbol right there, mathematicians love to come up with ways of summarizing things they say over and over again. And in math, you tend to say the phrase all real numbers over and over and over again, so you can't write that. I would stick to whatever Mrs. McCullough wants, and this is a great way. What notation is this called? Anybody remember? Something begins with an I? Yeah, interval notation, exactly. Generally speaking, it's great. What's the only complication when using interval notation? What can it look like sometimes? It can look like a coordinate, right? You just have to know the context. So looking at this function right here, what would happen if, so let's take this here. What does the -3 do to the function? It just moves everything down 3, right? Just moves everything down 3. So does that change? So this is going to be 0, -3 right there. Does that change anything about the domain? You know, it still extends infinitely left and right. It doesn't skip over anything. So the domain still says -infinity to infinity. But what about the range? If you looked at it sideways, does it skip over any y values? Does it skip over any y values? Meaning, are there any y values it can't be? I'll ask you this way. Does this ever stop going up? No, because you can always plug in a bigger number, right? The cube root of 1 billion, the cube root of 2 billion. You can always get bigger, right? Does it ever stop going down over here? No. So are there any y values that it does not cover? No. So what's the range going to be? Yes, that's correct. So that -3 doesn't really do anything. It moves this thing that covers everything down 3. Does it still cover everything on the y-axis? Yeah. Does it still cover everything on the x-axis? Absolutely. Is that always the case? No, it depends on the function. It totally depends on the function. Is there any value that you can't plug into the cube root function? No, it's an odd root, so you can plug in anything you want underneath that Radican symbol. So what's the domain of this going to be? I hate this. Yeah. Domain is just going to be all real numbers, and you guys like to write that as wrong brackets here. You guys like to write that as -infinity to infinity. Yes. What does so you haven't talked about graphing shifts, how this works, what happens here? You have, like, if what this graph right here is, it starts with the base graph for this is that cube root function, which looks like this. What does that -3 do? And that's a really terrible curve. I'm sorry, I apologize for that. It's still pretty bad, but you get the general shape, right? It should be symmetric. You should be able to rotate it 180 degrees. It's called symmetry around the origin. If you can rotate it 180 degrees around the origin, it would be the same thing. So that right there is the cube root of x. What do you think the minus 3 inside the cube root does? There are 4 options. It goes up 3, down 3, left 3, or right 3. You want to say left 3, right? You want to say left 3. It's either going to be left or right. It actually moves it to the right 3. When you go inside the radical, it goes the opposite direction you think it does. Because think of it, you're subtracting 3 before you do the cube root. So if you plug in, for example, 30, 30's height is going to be the cube root of 27. So when you plug in 30, it's really going to be the height of 27. So, for example, another way to think about this, when is this going to be 0? When x is 3, right? So that point, it used to be right here, but now where is that point? It's at 3. You've moved it to the right 3. So what does this function look like? Looks like this. Does the range change? No, it doesn't. So the domain and range are both the same. Cube root function, when you move it around, it's still usually going to cover everything unless you take something out. Take something out. The square root of x is equal to x to what power? 1 over 2. 1 over 2. The square root of x is equal to 1/2. Actually, there's an invisible number right here. Do you know what the invisible number is? It is 2. Okay, so what is the power for the cube root of x? x2. The power is 1/3. Correct. So the nth root of x, what is that equal to? X to the 1 over n, exactly. So if we go back over here, you can write the numerator as t to the 4th to the what power? What power is cube root? 1 over 3. So this is to the 1/3 power over t to the 4th to the what power? 1 over 5. So then, exponent rules that you already know, what do you do with powers of powers?
4 over 3.
So what's the verb? Give me a verb. That's the answer. You multiply. Thank you. You multiply. So this is going to be t to the what? 4 over 3 over t to the what? Exactly. So now, when you're sitting in that land, how do you simplify further when you divide and you have the same base? What do you do with the powers? No. When you subtract. There you go. So it's t to the 4/3 minus 4 what? 5th. Now that we're doing subtraction of fractions, what do you need to subtract fractions? You need a common denominator. What's our LCD going to be of these two fractions? 15. So to get 15 here, we're going to multiply by 3 over. And what do we multiply the other one by? 5 over 5. And what's this going to equal? T to the 20 over 3 minus what? Not 3. What is that? What's the base? 15. Thank you. 15 over 15. So you end up with t to the what? 8 over 15. Then you ask yourself, can you simplify that fraction? And the answer is, I don't think so. There's no common factors of 8 and 15.
She wants to put it back into the form like you do.
No, I understand that, but in this question it says simplify by first. I'm sorry, what am I looking at here? This is 8.2, number 59. Simplify by first converting to rational exponents. So we've simplified this. So if this right here would be the most simplified form, this is exponential form. If you want it in radical form, what root is that? How would you write that in radical form? Any ideas? The 15th root of what? 8th. There's actually a second way you can write it in radical form. There is a second way because you can reverse this. You could do the 15th root of t all to the what? 8th power. These are the same. You can do it either way. That's fine. What? We're going to add them, but it's going to turn into subtraction. You're absolutely right. So you're going to end up with x to the 2/3 minus 1/4.
Or should you subtract or add when they're multiplied and subtract when they
divide? Okay. That's correct. Yes, the reason this works, just so you can see why this works, this is the same thing as x to the 2/3 times 1 over x to the 1/4, because it's negative exponent. So if you had that, now you're in the bottom, now you're subtracting. It's the same exact thing. So when we do this out, you need a common denominator. You're going to multiply the first one by 4. So it's going to be 8 over what? 12 minus what? 3 over 12? X to the 5 over 12. My recommendation when you're attacking rational expressions like this is take it one step at a time. Don't try to do too much at once. So what could be a good starting point? What would you examine, or what would you do first? The body, yeah. Do the denominator first, right? And what do you do with those powers? Subtract. Thank you. K to the 1/3, so it's going to be k to the what? Negative 1/3. So then you subtract, but now it's going to be addition because you're subtracting a negative. So what's the final answer going to be, dice k? K to the what power? Yoku dekimasta? Is that how you say it, right? Did I get that right? I didn't tell you to shut up, right? I told you good job. It's always my worry. For 7 years, I would say be quiet in many different languages, and one of them was Korean, and it worked very well. My classes that had Korean students would be quiet very quickly. 7 years in, after hundreds of times using the phrase, a girl in my class goes, "You should not say that, Mr. Seamon." It turned out for 7 years I'd effectively been telling my Korean students to shut the F up. It worked really well. It worked really, really well. Yeah. Yeah. So I'd say something and they would be quiet. So I think I'm telling them to be quiet. That's the true story, everybody. It's a true story. 8.3. Any from 8.3? No? Yes? Maybe so? Okay. No. So what we have to do today, I'm trying to get a lot of information from Mrs. McCullough, but what last class did you cover any of 8.4? None of 8.4? Okay. So 8.4 is what we'll transition to right now. 8.4 is adding and subtracting rational expressions. Adding and subtracting rational expressions. So let's just start this here. Try this by yourself first. Mess around with it. Everybody, surface is flat. Surface is flat. Surface is flat. Take out your stylus. Work on this in OneNote. So work on these by yourself. It totally doesn't matter if you're right or wrong. I want to see what you can simplify to right now. 7 apples. Nice. 7√3. Wonderful. Oh, look. What about this one? This one's a little different. What's the challenge here? What radical, what root are we dealing with?
30.
The cube root, the third root. The third root. So you're looking for a factor of 16 that is a cube. I don't know if you've done this with Mrs. McCullough, but one thing I like teaching my students is you start factoring by just pulling out the smallest number you can. What's left if you pull out a 2? 8. And then what can you pull out of 8? 2 and 4. And then you can pull out a 2 and a 2. If it's a cube root, you're looking for a cube. Do you see anything there that's repeated 3 times? Yeah, you have this right here. So one way you can rewrite this is 2 times the cube root of 2, and this is the long form way of writing it, times the cube root of 2 times the cube root of 2. You can expand it. But what is the cube root of 2 times the cube root of 2 times the cube root of 2? What's the square root of 5 times the square root of 5? 5. What's the square root of a table times the square root of a table? A table. What's the cube root of 2 times the cube root of 2 times the cube root of 2? Is 2. It is 2 because it's the cube root and you're multiplying by itself 3 times, so you effectively get rid of all of them. So what does that mean this equals? This 2 right here. Everybody see this 2 right here? That 2 is along for the ride. It's already out there. But all these ones right here that are in the green right here, what do these 3 equal when you multiply them together? 2. And then you're still left with 1 cube root of 2, and this one comes down. So how many cube roots of 2 do you have now? How many cube roots of 2 do you have? 4 of them. So this equals 4 times the cube root of 2. Do you see these parentheses I'm putting around the cube root of 2? Why did I do that? Why is it kind of important to do that? 4 cubed times the square root of 2. It's not the same thing. It really isn't. 4 cubed is 64. It's a lot bigger. So we go back to here. 54. Can you factor 54?
Yeah.
Say yes. That's correct. So you're going to have 5 times the cube root of what's half of 54? 27. Oh, it's 2, right? Not 3. Go right ahead. Yes.
So 54 is like 9 times 6, right? So why don't we just write 3?
Because I'll show you. I'll tell you. This is why. We're looking for something that's a cube because it's a cube root. What is the cube root of 27? That's why I went to it. If it was square root, absolutely, you'd look for a square. But you're looking for a cube now. So what is this going to be? 5 times 3 times the cube root of 2? So how many cube roots of 2 do I have here? 15 of them. Now can I add these together? I have this and I have this. Now can I add them together? Sure can. How many do I have? 15 of them and 4 of them. So I have 19 times the cube root of 2. Converting this into exponential form is my favorite way to do this. So you're going to have 2 times x squared y to the 1/3 plus 8x to the 5th y to the 4th to the 1/3. What can you do with the power now? What can you do with the power? Powers of powers, what do you do? 4 squared to the 8th. What do you do with the powers? You multiply them, right? So over here, what do you do with this 1/3? You distribute it in both places. So what is it going to be? 2 times x to the what power? 2/3. Y to the what power? 1/3. Oh, I'll do that consistently. Sorry, let me do that a little better. 1/3. Here we have 8 to the times x to the 5/3, y to the 4/3. There's one number there that we can simplify. Which one is it? Which number there can we simplify? 8 to the 1/3. What is the cube root of 8? 2. So we're doing this step by step here. The challenge is that at this point, can we add anything together here? Do we just have apples? Really? Is 2/3 the same as 5/3? But what do you notice? What's the opposite? And this is a little bit of a tricky question. What's the opposite of multiplication? Hint, not division. Multiplication is taking 3 times 4 and getting 12. If I asked you to do the opposite, you'd go from 12 and you'd come up with the, begins with an F, you'd come up with the factors. So the opposite of multiplication is factoring. When you factor, raise your hand if you factor. It's my favorite thing ever. So you have to like it too. You have no choice. You have two expressions here. You have this expression and you're adding it to a second expression. Do they have things in common? What's one thing they have in common? They have x's and y's and they have a 2. So what could you factor out first if you wanted to? You could factor out 2. So this equals 2 times x to the 2/3, y to the 3rd, plus x to the 5/3, y to the 4/3. Now you also said, what else do they have in common? They also have an x in it and they have a y in it. So if they have x's and y's, you want to take x out, but you want to take x out that's the highest power or the lowest power? You want to take out the x that's the lowest power. Which is lower, 2/3 or 5/3? So if you take that out, what do you end up with? 2x to the 2/3 times y to the 1/3 plus x to what power is left? What power of x is left? It's x to the 3/3, which is just x. Because 2/3 and 3/3 is 5. Well, 2/3 and 3/3 is 5/3. I went backwards here, so you're left with just x. I'm leaving it there so you can disassemble this. You're going to have these notes and it's being recorded, so you'll get both. What else can we pull out now? What's the next thing we could pull out? To the what power? Yeah. So you have y to the 1/3. What does that leave you with? What's the first thing here going to be? 1. Good. Plus x, y to the what power? If you take 1 away, from 4/3, what do you left? 3/3, which is? So this right here would be the most simplified form. Is this an easy problem? No. This is challenging. This is definitely challenging. This is not meant to be just straightforward easy. It's challenging. Can you do anything with that one? No, not really. I mean, you want to. You know they're not apples. You're like, oh, I want to make them into apples, right? The problem is 3 is what type of number? Prime. 5 is. So there's no nice way to combine these. Sometimes there just is no nice way. You would just say this is most simplified right now. So if they ask you to simplify, you just write it again. Well, if they're prime, you can stop. I'm just saying one thing that math books do is they'll sometimes say it's impossible to do something. It's not that it's impossible, it's just that you need higher math. What I mean by this is theoretically, can you break this up into, everything has square terms, but it turns it into fractions. And does it make it simpler if we suddenly generate fractions? Generally, no. Generally, no. So if you get a problem like this, you can say, it is most simplified. Just write it again. Do this first one right here. You end up with 2 times the square root of 5 times the square root of 4 times the square root of x. I'm expanding it too much just to show you. Because what is 20? 5 and 4. Well, what is the square root of 4? 2. So what do you end up with? 4 square roots of 5x. And what about this over here? It's minus the square root of 9 times the square root of 5x. What's the square root of 9? So you have 3 root 5x. So you have 4 root 5x minus 3 root 5x. What do you end up with? Square root of 5x. You see what happens there? You can kind of have faith that most of these are going to work out, and they're not going to lead you into total dead ends. But generally speaking, are you always going to be able to combine nicely like this? Not always, no. If I asked you to multiply this, there's an acronym that sometimes comes to mind when you multiply things like this. FOIL. Sometimes math teachers don't really like that because FOIL only really works when you're dealing with 2 terms and 2 terms. Theoretically, could you multiply 3 terms times 2 terms? There'd be like a middle term and you need a new acronym. I like saying you have to multiply everything in the first times everything in the second. But FOIL helps kind of standardize the order. Not much changes. You know the mechanism for simplification. So the first multiplication is going to be root 5 times root 6, which is what? Root 30. Then you have root 5 times 1. So that's just root what? 5. And then you get 3 root 6. And then you get what? 3. Is there anything we can combine there to simplify? Is the next question you have to ask yourself. Is there anything right there that we can simplify?
30.
The 30 is, you want to break it up, you could make it root 5 and root what? 6. Technically speaking, sometimes, have you ever gotten to the point where you're not sure if something is most simplified? Probably in your life you've gotten to the point where something, you're like, I'm not sure if it's most simplified. There's lots of different things you can do to rearrange this, but there's no one good method that says this is the most simplified. You might be tempted to start like factoring things, like you can pull out a root 5 here and you can pull out a 3 there, right? But then guess what you end up back at? This. You end up back where you started. So the only thing really right now you need to remember is when you multiply these out, this right here is probably what your only answer is going to be right now. That being said, if you got like 5 and 6, should you add 5 and 6 together if they were by themselves? Sure, you take the easy stuff, the low-hanging fruit, but don't sit here don't try to factor this because you just took the factored form. I've seen that happen before. Kids work really, really hard and then they end up right back where they started, which actually is kind of cool because it means they probably did it right, but they ended up where 7. Yay! So does it work out sometimes and make your life nicer? Sure, absolutely. Let's see if there's a one that it is k minus m. Does that match what we just did up here? 10 minus 3 is 7. Yeah, it does match. So it should be k minus m. The last section here, there's a lot more. Yeah, oh, actually, not too much more. Something you commonly have to do is you have to do something called rationalizing the denominator. The reason it's called rationalizing the denominator is any square root that isn't the square root of a perfect square is an irrational number. What's a rational number? What are the first 5 letters of rational? Spell it for me. Ratio. A rational number is a number that can be written as of integers. What's an irrational number? Any number that can't be written as a ratio of integers. So for example, pi is irrational. Another way to say it is it extends infinitely without pattern. There's no pattern to it, because if there's any pattern, you can write it as a fraction. So rational number, no ratio. Irrational number means no ratio. So one common thing you have to do for various reasons is rationalize the denominator without changing the overall value. So you're going to come up with an expression that's the same value but does not have a radical down here. You can only multiply by what number? Different forms of the number 1. So what can you multiply root 7 by to make it not a root anymore? Root 7. But if you multiply by root 7 in the denominator, what do you have to multiply by on the top? Yeah, so this right here is just a fancy form of 1. So you end up with 3 root 7 over 7. What is root 7 times root 7? 7. So nothing really changes over here. Remember, you only care about rationalizing the denominator. So what do you think you multiply this one by right here? Root 5 over root 5. Say the whole thing. So what do you end up with? 5 root what? Over 5. Oh wait, does something cancel? Yeah, it actually equals root 10. That's kind of cool. Nice. Does anything really change mechanically here? This one, what do you multiply this one by? Over root 12. Not saying the denominator is the equivalent of like dropping the period on a sentence or just taking out the verb in a sentence. You can't multiply by root 12 because that'll change the value. Now, it gets a little bit more complicated because you could not just have a square root. What could you have instead? A cube root? So let's think about this for a second. We're trying to multiply by something that turns this into over 2. What do you have to multiply the cube root of 2 by to get 2? You need 3 of them, right? So you're going to multiply by the cube root of 2 and the cube root of 2. Because what is 3 of them multiplied together? 2. But if you multiply by the cube root of 2 and the cube root of 2 in the denominator, what do you need to multiply by on the top? The same exact thing. So you have cube root of 2 and the cube root of. So you end up with 5 cube root of 2 cube root of 2. What power is cube root? 1/3. So if you have 2 to the 1/3 times 2 to the 1/3, what does this equal? What is 2 to the 1/3 times 2 to the 1/3? 2 to the 2/3. So one way you can write this is, if you wanted to, 5 times 2 to the 2/3 all over what? All over 2. You've rationalized the denominator. You've rationalized